Our question wants us to consider this equilateral triangle here, where each side, A, B, and C, is equal to length L, okay? And the charges here are represented by red dots at each corner of the triangle. And it wants us then to find the potential at each midpoint of the sides of each side, okay? Well, the distance from one corner to the opposite midpoint, which I write in the green line as D, from the fact that this is a 30-60, that would make a 30-60-90 triangle, right? Because this would be 90 degrees here. And we know that an equilateral triangle, each side has an angle of 60. So then half of that for the top left corner would be 30. So it's 30-60-90. So that distance there, D, would be root 3 over 2 times L. Okay. Well, then using this, we can go ahead and solve for the potentials at each corner. We're going to call the first potential at point A here, VA. And that's going to be equal to, well, you have potential is K times the charge here. The charge would be minus Q. So this would be multiplied by minus Q divided by the distance. Well, the distance here would be half the length from that top left corner. So it would be L over 2. Plus, then you have the other one, the other corner, which is K times the charge, which is Q, or excuse me, minus 3Q. So instead of a plus, you can just write a minus sign out here. So it'd be 3 times K. Well, let's write it like this because the charge will let you know where the charge is coming from. This is K times the charge, which is minus 3Q. So of course you could have pulled that negative sign out front, but we'll just keep it in the parenthesis, divided by L over 2. So that's the distance from that corner. Plus the last one is K times the charge here, which is just positive Q. So you can just write Q, divided by the distance to that, from that corner to the midpoint of A is the distance D, which is root 3 over 2 times L. So plugging all these values in, we find that this is equal to negative 6.85 times K times Q divided by L. We can box that in as our solution for the potential at the midpoint of side A. Okay, now we can do the same thing to find the potential at the midpoint of side B. This is going to be equal to, the first one is K times negative Q. That's the charge in that corner, divided by the distance, which is L over 2. Plus the charge in the next adjacent corner is Q. So it'd be K times Q divided by L over 2, plus the charge in the opposite corner, which is minus 3Q. So I'm just going to pull the minus sign out front this time, since you know what I'm doing. So this is K times 3Q divided by, and that one is the distance D. So plugging all those values in this expression, we find that this is negative 3.46 K Q. Let's rewrite that K to make it a little neater. Divided by L. We can box that in as our solution for the potential at the midpoint of side B. And lastly, the potential at the midpoint of side C. We have the first adjacent corner, it's K times that charge, which is Q, divided by the distance, L over 2. Okay. Plus the next adjacent corner, which is minus 3Q. So we can just pull that minus sign out front. So this is, we can pull the 3 out front as well. So this is 3 times K times Q divided by that distance, which is L over 2. And then in the far corner, we have minus Q. So this is going to be minus K times Q divided by that distance, since it's the farther corner, which is D. Plugging all those values in this expression, we find that this is minus 5.15 K Q over L. We can box that in as our solution for the midpoint of side C.